Welcome to the Explainer. If you've ever stared at the periodic table and felt totally overwhelmed, well, you are definitely not alone. It looks like a giant, intimidating wall of letters, right? But today, we're going to catalyze your understanding. We're going to uncover the hidden patterns that dictate how literally everything in our universe behaves, completely transforming what looks like random data into your ultimate predictable scientific cheat sheet. Let's dive in. Here is our game plan for today's Explainer. First, Mendeleev to the modern table. Second, decoding the periodic grid. Third, Group I alkali metals. Fourth, transition elements and noble gases. And finally, mastering periodic trends. Okay, Section 1, Mendeleev to the modern table. We're starting our journey back in time with a brilliant Russian chemist named Dmitry Mendeleev. Now, while everyone else was just trying to make simple lists of elements, Mendeleev noticed something huge. He realized that the physical and chemical properties of elements actually repeat in a perfectly predictable pattern. He started ordering them by their atomic weight, but here was his true stroke of genius. He didn't force things to fit. If a spot didn't match the chemistry he expected, he just left a blank space. He successfully predicted undiscovered elements like gallium before anyone had ever seen them. Now, his table wasn't entirely perfect. It couldn't account for isotopes, but the modern table we use today perfected his grid. By arranging elements based on their atomic number, meaning the number of protons, we elegantly removed all those gaps and divided the table into specific electron blocks, like the S, P, D, and F blocks. Moving right along to Section 2, decoding the periodic grid. To use this map effectively, we first need to get a handle on its basic coordinates. Think of it like latitude and longitude. The modern table is made up of 7 horizontal rows, which we call periods, and 18 vertical columns known as groups. When you move across a period, you're looking at elements that have the exact same number of occupied electron shells. But the real magic happens in the vertical groups. Elements in the same vertical column share very similar chemical behaviors. Why? Because they possess the exact same number of outermost electrons. It's those outer electrons that completely dictate how an atom interacts with the world around it. So, now that we know how the grid works, I've got a bit of an explosive question for you. What happens when you take an element from the very first group on the far left of the map and just drop it into a bowl of water? Spoiler alert, do not try this at home. Let's see what happens. Section 3, Group Alkali Metals. Over on the extreme left edge of our map, we find Group I, the alkali metals. We're talking lithium, sodium, and potassium. Now, when you hear the word metal, you probably think of something heavy, hard, and indestructible, right? Not these guys. Group I metals are total rule breakers. They are incredibly soft. You can literally slice right through them with a butter knife. They also have such unusually low densities that they will actually float on water. And chemically speaking, they have one massive overarching goal in life. They are highly eager to lose one electron. Because electrons carry a negative charge, ditching one leaves the atom with a net positive charge, forming a +1 ion. Let's go back to that bowl of water. When lithium hits the surface, you get a relatively slow fizzing as it dances around. But step down one spot on the grid to sodium, and the reaction drastically ramps up. It darts rapidly across the water and quickly dissolves, pumping out hydrogen gas. Step down again to potassium, and it reacts so aggressively that the heat instantly ignites the hydrogen. Boom, a bright, blazing lilac flame. The absolute crucial takeaway here is that in chemistry, reactivity is not random. It is incredibly predictable. It strongly increases as you move down group 1. So elements at the bottom, like rubidium sparking or cesium creating a violent explosion, are far more reactive than the ones at the top. But why does this actually happen? The secret behind all of this explosive behavior really just comes down to a single number: 1. Every single group I element has exactly one lonely electron sitting way out in its outermost shell. As you move down the group, you're adding a whole new shell of electrons every single time. This means the atom gets physically larger. Its atomic radius increases. Think of the positively charged nucleus and that outer electron like 2 magnets. As you pull them further apart and stuff more and more layers of electrons between them, that magnetic attraction gets significantly weaker. It becomes incredibly easy for that outer electron to just get snatched away. And in chemistry, easily losing an electron means a massive, often violent reaction. All right, Section 4, Transition Elements and Noble Gases. Let's pan across our map and contrast two completely different chemical families. Sitting right in the middle, in what we call the D block, are the transition elements. This is where you find your iron, copper, and manganese. Unlike Group I, these are your classic everyday heavy metals. They boast high densities and high melting points, but chemically, they're incredibly versatile. They frequently act as catalysts to speed up reactions, they form beautifully colored compounds, and they have variable oxidation numbers, which basically just means an element like iron can form entirely different types of bonds. This is exactly why the flaky orange rust on a piece of scrap metal looks completely different from the iron pumping through your red blood cells. Now, jumping all the way to the far right edge of the table, we hit Group 8, the noble gases. If the alkali metals are the explosive social butterflies of the chemical world, the noble gases are the absolute loners. Elements like argon and neon exist as monatomic gases, meaning they just float around as single, solitary atoms. They are incredibly stable and famously inert, meaning they're highly unreactive. That inertness is precisely why we pump argon into light bulbs and neon into bright, glowing signs. They safely conduct energy without bursting into flames. Their secret? It is all about the number 8. They have a completely full, perfectly stable outer shell of exactly 8 electrons. Because their outer shell is full, they don't need to lose, gain, or share electrons with anyone else. They have achieved ultimate chemical stability, meaning they have absolutely zero desire to react with anything. Section 5. Mastering Periodic Trends. For our final section, let's zoom all the way out. Now that we understand how specific neighborhoods function, a primary divide emerges that lets us predict behavior instantly. On the left side, we have the metals. They typically have 1 to 3 outer electrons, form basic oxides, and are fantastic electrical conductors, which is exactly why we use copper for electrical wires, but never sulfur. Then, on the right side, separated by a sort of zigzag line, we have the nonmetals. These guys have 4 to 7 outer electrons, form acidic oxides, and are famously poor conductors. So here is the overarching trend. Because atoms on the left want to lose electrons, and atoms on the right want to gain them, the metallic character literally fades away as you read from left to right across the grid. Conversely, because atoms get larger as you go down, making it much easier to lose electrons, the metallic nature logically and predictably increases as you move down a group. But wait, this is chemistry, so there is almost always a fascinating exception to the rule. Let's look at Group 7, the halogens, elements like fluorine, chlorine, and iodine. Notice how this is the exact opposite of our Group I metals. For halogens, the reactivity actually decreases as you go down the group. This means the element at the very top, fluorine, is the most aggressively reactive.
Why the flip? Well, remember that metals react by tossing away an electron? But halogens, sitting over on the right, have 7 outer electrons. To reach that magical, stable number 8, they react by snatching or gaining an electron. It is basically a microscopic tug of war. As the atom gets bigger down the group, the positive pull from the nucleus is buried under more and more electron shells. This makes it physically harder for the nucleus to reach out and steal an extra electron from another atom. So the smaller the halogen, the closer its nucleus is to the outside world, and the more violently it reacts.
Which leaves us with this final thought. Based on the map of matter we've just decoded, think about the ultimate matchup. If francium is sitting at the very bottom left, meaning its outer electron is practically falling off, and fluorine is sitting at the top right, meaning it has an overwhelmingly powerful pull for a new electron, what do you think would happen if the universe's most eager giver of electrons met its most aggressive taker? Well, knowing your new periodic trends, I bet you can predict it'd be one seriously explosive reaction. Keep bonding with these concepts, keep questioning, and I'll see you in the next explainer.